And so we started last day. We talked about bus arbitration. We talked about masters and slaves on the bus. You know, it's basically a roadway that can only carry one car at a time. And so if the processor and other devices attached to the bus want to send information on the bus, we talked about how there has to be a method or a process by which we don't have collisions on the bus. Only one master can be in control of the bus at any particular time. And we talked about bus arbitration and that sort of thing. So let's talk a little bit today about how buses, there's two different types of buses. There's synchronous buses and asynchronous buses, and how information is managed over those. It's a relatively complicated topic, and the textbook and what we do here and I'm just mimicking exactly what the textbook says here. So if everything I say today sounds like gibberish, just go to the textbook and read it, and hopefully that's better. But I'm following the textbook. The figures are all from the textbook. And it's really just giving examples at a high level of what happens on a bus. There's a whole lot more detail that goes on underneath. And the whole exercise of designing a computer system and the bus and how the signals travel over the bus is a pretty complicated process. We're just sort of hitting the high points so that you have an appreciation or a sort of basic understanding of what goes on a bus and a computer. Okay, so and sort of what we're looking at is basically examples. They tend to work like this in most cases, but of course there's things that there's details that we just won't cover. Okay, so we're going to start with synchronous buses, and a synchronous bus is synchronized, meaning that all of the devices attached to the bus are going to be doing things at certain points in time. Okay, so in order to do that, everybody has to be synchronized to a clock signal. So on the bus, again, there's three different types of information or bus lines, if you want to call them that. There's the data lines over which data is transferred. There's the address lines over which the addresses in memory or registers in devices are transferred. And then there's control lines. And one of those control lines is what we call a clock signal. Okay, and everybody's familiar with, you go out and look at a specification for a computer that you want to buy, and it tells you how fast it's running, right? That is the computer clock. And that clock is a square wave, and that square wave has a certain frequency, and that is what is termed the clock in the computer, and that is one of the signals that is transferred on the bus so that all devices can see this control signal. And and in a synchronous bus, things happen on edges or transitions of the clock. So obviously the faster the clock, the more quickly things happen, because transitions come more often. But there are limitations, as we'll discuss. Okay, so a synchronous bus, everybody is looking at this clock, and everybody knows, and when I say everybody, I mean all the devices connected to the processor, they all know that things only happen on the edge of the bus. Okay, so that's when they do stuff. So in its most simplest form, in this case, most of the time the examples and the figures we're looking at are for a read instruction. So for instance, the processor is reading a value out of memory and bringing it into a general purpose register in the processor. So for a read operation, and we didn't talk about this one last time, did we? Or did we? I forget now. Nobody remembers, so we'll do it again. You don't recall doing it last time? You have some notes. Well, we'll go over it again just to remind ourselves. So things happen on the edges. And because I remember talking about what these different figures mean, right? These just mean there's a number of lines on the address bus, and on the command or control bus. Command is just another word for control. And some of them are high and some of them are low, so we indicate that with a 0 and a 1. Okay. When there's a transition like that, that obviously means that the information on these buses is changing at this point in time. Okay. So in this particular case, on the rising edge of the clock signal, the master, the processor, for example, is going to put an address on the address bus, the address that the processor wants to read from memory, and they're going to put some control information on the control bus, basically telling the processor this is a read operation, for example, okay? So that's going to be valid during this, during the whole cycle, okay? As soon as this information goes on the address bus and on the control bus, all the devices connected to the bus are going to be looking at that and decoding it, okay? Okay, well, there's an address there. Is that an address that's part of my address space? Okay, well, is what all these other devices, external devices connected to the bus are doing. So the one device, say the main memory unit that recognizes that address, will then go to that address. It will get the value that's there, and then on the next transition of the clock, this downward edge, it will put that data on the data bus, which is indicated by this here. Okay, so there's no valid data up to this point, and then at this point, the memory unit puts the data on the data bus, okay? So something happens here, the master puts information on the bus, something happens here, the slave, the memory unit, puts the data at that address on the bus, and then on the next edge of the clock, the master reads that into to a register, and then it changes the address and command information, maybe to read the next word in memory or to do something else. Okay, so it takes one bus cycle to read one thing from memory in a read operation like this. Okay, so in its most basic form, that's what happens on a synchronous bus. Nothing, well, I won't say nothing, but nothing changes on the bus during the time in between these transitions. Right? Obviously, stuff is happening in here. For instance, during this part of the cycle, the memory unit is decoding the address on the address bus, and it's going to that address in its internal memory and getting the value that's happening in here. But in terms of activity on the bus, that only happens on these edges, okay? All right, so that's a review of what we did last day. So this is the same figure, but the question is, well, if things only happen on the edges of the bus, why not just increase the clock frequency a whole lot so things happen a whole lot faster and your computer's faster? Well, the problem is that because stuff is happening inside of these cycles, between the transitions, we can't just make the bus frequency, the clock frequency higher, okay? So for instance, in the most basic, most basic delays are the processor puts this information on the bus at this point in time, but it takes a little bit of time to get down the bus, even though it's traveling almost at the speed of light. It takes a little bit of time for those signals to travel down the bus and hit that memory unit, okay? So propagation delay. And you know, we make this big, but you know, this is like nanoseconds or microseconds maybe. The other is decoding delay. It takes some time, even once these signals hit the main memory unit or arrive at the main memory unit, that main memory unit, the circuitry in it that decodes that address, determines, yeah, that's my address, and goes and gets the data from memory. That especially takes some time, as we'll talk about when we talk about memory after the break. That is the decoding delay, because at this clock edge, the slave, the master, or pardon me, the memory unit had to do a couple of things. It had to decode the address, had to recognize the address, had to go to that address, get what was there, put it on the bus, so that at this edge, that data appears on the bus, okay? That takes time. So you just can't make this as short as you want. On the second half of the cycle, again, there's propagation delay. This time the data has to find its way, it has to travel back on the bus, on the data bus, back to the processor. That takes amount of time. And then once that data hits the input to the processor, we have to wait for what's called the setup time, right? When you have a flip-flop, everybody knows what a flip-flop is, right? And maybe you've studied setup time and hold time for a flip-flop. Have you heard of those terms before? Okay, well, basically it takes a little bit of time. That data at the input to a flip-flop has to be there for some period of time before it will be latched into the flip-flop. It doesn't happen instantaneously, okay? So uh, that, that's part of this delay that you have to wait for, okay? Because at this point in time, you know, these signals are going to be changing. At this edge of the clock, it's assumed that the data is now in the processor. So you have to give the processor flip-flops a little bit of time to load that data in, okay? On the other side, you have what's called a hold time, which we're going to talk about in a future slide. Let's forget about that for now. Okay, so that's why the or the clock frequency can't just be as fast as you want, okay? And so obviously, you know, computer designers, they're trying to minimize these delays as much as possible so you can increase the clock frequency, okay?
Constant for a whole period of the bus clock.
Yeah.
Is there a reason that, I can understand that for the command line, you know, you can keep maybe your computer in one state for the duration of the instruction, but why does the address line have to stay there as well?
After this point of time, it really doesn't have to, but I think it's just for sake of simplicity that they just leave it like this, right? There's no reason to change it because at this point in time, the processor, well, you know, you could make an argument that, well, why not put a new address here so that the next device can start working on it, right? The only problem is, what if that address is for the same device, right? So I think that's why they leave it there. There's no reason to change it at this point. It doesn't benefit you. So just for simplicity, you only change it when you're ready for the next one. So that's the best I could answer, okay? Very idealized picture of what's going on, right? In reality, back here, if we go to the, no, let's see. All right, so, but that's not the whole story. Yes, sir?
When you have the address.
Okay, well, you know, this is, because there are propagation delays down the bus, the master and slave don't really see things happening at the same time, okay? So the bus clock here, we're going to assume is seen the same by the master and the slave. And that's a big design consideration. They put a lot of effort in making sure that everybody, you know, especially if it's a synchronized bus, obviously, that every device connected to this clock signal sees these transitions at the same time, right? It doesn't help when, in the spy movie, when they try to synchronize their watches and they're all 15 seconds different, right? You want to make sure everybody's seeing these transitions at the same time. But in terms of the other buses and the other signals traveling down the bus, that's not necessarily true. So for instance, if this is when the command and address signals actually change are changed by the master or are seen on the bus from the point of view of the master, it takes a little bit of time, this difference in time, before that same transition is seen by the slave, right? So that's basically the propagation time. Okay, so if we look at what's going on, again, things tend to happen on the edges, but now there's delays. So at this point in time, yes, the master is going to change the address and command information on the bus, but it takes a little bit of time because of the output circuitry of the processor before that information actually hits the bus. Okay, so yes, the processor does it at this time, but there's delays in the circuitry, okay? And so it takes a little bit of time before it actually hits the bus, okay? And then there's a little bit of propagation delay before the slave sees that change of address and command information on the bus, okay? So even though theoretically it's happening here, the slave doesn't actually see it until this time later, okay? So there's the propagation delay, and now, of course, you need decoding delay, okay? So the slave sees this information, it starts decoding it right away, takes some time to do it, and again, it gets the value from memory, wants to put it on the bus now, it does so theoretically at this time, but there's a little bit of delay again because of the output circuitry of the main memory unit, okay? So that data doesn't actually hit the bus until some short time later after this transition, okay? Again, we have a small amount of propagation delay down the bus. So the master, the processor, doesn't actually see that data change on the data bus until this point in time. Okay? And then now again, it has to, we need a certain amount of setup time. That data has to be stable on the inputs to the flip-flops, on the input circuitry of the processor. And then it's going to latch it in. And then we have what we also call hold time. So here we've got some flip-flop setup time. And here we have flip-flop hold time. So again, at this transition, the slave says, okay, I'm done. I can take the data off the data bus. Again, there's a little bit of delay, okay, because of the output circuitry before it can change that. Okay, I guess I should have started up here. At this transition time, the master said, okay, this read cycle is over, so I can change the address and command information for the next read that's going to happen in the next bus cycle. Again, there's a little bit of delay because of output circuitry. Okay, this change in address and command information, again, due to propagation delay, arrives at the slave a little bit later. Okay, and the slave, again, at this time says, well, I can take the data off the bus because I'm at the end of this particular cycle. Okay, and there's a little bit delay there. Okay. So in actuality, yes, we think that everything's happening on these edges, but because of delays, it actually isn't, okay? And it's very important in a synchronous bus that these delays are taken into account so that things don't happen, certain things don't happen before other things, okay? Okay, so that's synchronous bus. So this one, right? After the slave receives the address information, it has to decode it, okay? If a particular slave is really slow at doing that, well, then you have to increase the period of this clock cycle in order to accommodate that, okay? So it comes down to how long does this cycle have to be? It has to be long enough to accommodate the slowest device on your bus, okay? So obviously that means faster devices are slowed down to the speed of the slowest device, obviously. Okay, so back here, whatever is on the data bus at this point in time, the master's going to read it in. Okay, it doesn't know whether that data is actually the data of the address that it specified at the beginning of the cycle. There's no way for it to know that. Okay, it just says, okay, at this clock edge, I put the address information on. On this clock edge, I read the data bus, whatever's on there. And it assumes that that's valid data. We have no way of knowing that, though. Okay, so that's another problem. So there's still a few problems, though. Problem number one, because a transfer has to be completed in one clock cycle, the bus clock cycle would be limited to the speed of the slowest device and longest delay. Undesired problem we have. Second problem, we currently have no means of knowing whether or not the I/O device responded and placed valid data on the bus. So how can we get around these? Well, some extra control signals are used in what we call handshaking. Okay, and handshaking is basically the concept, you stick out your hand to shake somebody's hand, they reciprocate by extending their hand and you shake hands. Okay, it's the same kind of thing. So it provides a validation for a successful transfer, and it also speeds things up for fast devices because it allows us to have multi-cycle transfers. We'll talk about that in a second. We can use a higher frequency clock if we use multi-cycle transfers, so that faster devices can, if you're communicating with a faster device, it can go faster. If you're communicating with a slower device, it can go slower, so it becomes more flexible. Okay, so that's, okay, so here's the same kind of stuff, but we're going to introduce this slave-ready signal. Okay, so same thing, here we got a clock, here we got the address. The address and command lines have been separated, although it doesn't really matter, they're happening at the same time. Again, we've got a data bus, right, where the, and this again is a read operation, say the processor is reading something from memory, but now we're gonna add this handshaking signal, this slave-ready signal. Okay, and it solves the two problems we have. First of all, how does the processor know that there is valid data on the bus? Well, again, the processor is going to put address and command information on this edge onto the bus. Again, there's a little bit of a delay because of the output circuitry, right? All the devices on the bus start decoding it, okay? And this particular device, after it decodes it on this edge of the clock, it's going to go to that address and get that data, okay? And this particular device took one cycle to do that. So that on the next edge, it can put data on the bus. And again, there's a little bit of delay because of output circuitry, okay? At the same time, it asserts the slave ready signal. So the master puts the address and command information on the bus, and now it waits. And what is it waiting for? It waits for the slave ready signal to go high. So when it sees this slave ready signal to go high, on the next edge of the clock, it's going to read in the data that's on the data bus, okay? On this edge, it's not going to, the master's not going to do anything. The processor won't do anything because this is still low. So it knows there's not valid data on the data bus yet. When it sees this go high, it says, okay, now there's valid data on the data bus. On the next edge of the clock, it's going to read that data in, okay? So that handles the problem of how does the processor know there's valid data. What about slow devices versus fast devices? Well, in this case, this particular device took one clock signal to go and get the data, okay? Maybe a really slow device takes two clock signals to get the data, in which case it would not raise its slave ready until this cycle here, okay? Well, that's okay. The processor waits two clock cycles, and then it sees the slave ready signal go high, and it knows there's valid data, and it reads it in, okay? But if the device is faster, say we got a really fast device, it decodes here, and it takes almost no time to get that data onto the data bus, maybe it asserts the slave ready here, in which case, at that point in time, the processor, or if in that case, the processor is going to read the data in on this clock edge instead of this clock edge. Yes, sir?
How does the slave know the data's been read in?
How does the slave know the data has been written?
Has been read into the, read in by the processor. Like the slave ready's going low again. How does it know that it's?
It just waits for one. It takes it off on this, right? It puts it on here and it takes it off there. So it doesn't know in this case, right? We're going to look at asynchronous buses later, in which case that consideration is handled. Okay, so again, what we call a multi-cycle transfer. In this case, it took, 1, 2, basically 3 cycles of the clock to read it in. A slower device, it might take 4 cycles. A faster device, it might only take 2 cycles. Okay, and it's just because of this, the processor knows, it just monitors this. When this goes high, it goes, data's ready, next clock edge, I read it in. If it's got to wait 2, 3, 4 clock cycles, it does that. If it only takes 1 clock cycle, well then that read transfer only took 1 clock cycle. Okay, so that's what a multi-cycle transfer is. Right, this stuff goes to the slave, this stuff goes to the master, and we're done. Okay, so, master to slave, slave to master. Okay, so that is basically synchronous buses. All right, so let's move, in this case, on now to asynchronous buses, which, as the name suggests, doesn't use a clock. Things do not happen in a synchronous fashion. And there is so much going on that I have to write some notes down. Otherwise, there's no way you can remember it. Okay, so instead of a clock now, we're going to use a full handshaking type of scheme. So more control signals. So you're going to now just not have a slave ready, you're also going to have a master ready. So basically, whenever one device does something, the other device responds, okay? So it's a full handshaking or a fully interlocked system. every device always acknowledges the other device. Okay. So let's take a look at what's going on, again, for a read operation or an input operation. So you'll notice there's no clock now, right? We call this a bus cycle only because it's one cycle for a whole read operation, okay? The read operation starts here and it basically ends here, okay? But there's no clock being used. So again, we have data lines and we have address and command lines. So a lot of stuff is exactly the same, right? At this point in time here, again, let's assume that the master is the processor and it's reading in data from the memory unit. So at this point in time, the master is going to place new address and command information on the address and control bus. Okay, so the address goes on right here. As soon as the other devices on the bus see that address information, as soon as it arrives at those devices, they immediately begin decoding it. Okay, so they're always actively monitoring that address bus, looking at that address, decoding it to try to recognize whether it's an address in their address space or not. Okay, so that happens right away. Okay, the next thing that's going to happen at time t1, so address put on the address bus. And the devices start decoding. Okay, at time t1, the master is going to assert its master ready signal, right? And this is done to tell the devices, hey, there is new valid address, address information on the address bus. Okay? Okay, well, why doesn't the master do it right here at the same time as it puts that new address on the address bus? It is to accommodate something called bus skew. Okay? You don't want to tell all the devices that there's a valid address on the address bus before all the devices have received it. Okay? Now, there's many devices connected to the address bus. Some of them will be closer to the processor, some will be farther away. So the propagation time will vary. Okay? And again, these look like really long times, but we're talking about very, very, very short times, right? Yes?
Doesn't that mean you have to know exactly how long each device takes to receive the data?
Yep. Yep.
It seems like a headache.
It is a headache, yeah. Designing buses is not an easy thing, from what I can tell. It's not for the faint-hearted, okay? So bus skew, again, is the difference in propagation time when a signal is sent out by a single source to multiple receivers, and it takes different amounts of time to get there. That's what we call bus skew, okay? So basically, you've got to wait until before all of the devices have received this information, before you can tell them, hey, I'm ready. There's valid data there, okay? You don't want this to happen too soon, because for some, they won't have some will have seen the new data, and the new data won't have arrived yet. And if you tell them there's new data there and they haven't seen the new data yet, they'll use the old data. Okay, so you gotta wait. Okay, also, you want to wait for decoding to happen. Okay, so this has to take into account bus skew and decoding delay. So you want to give the devices enough time to actually get the full address information and decode it. And then the master asserts its master ready, okay? Okay, these arrows here are a cause and effect type of a relationship, okay? So when the master ready signal goes up, when the processor asserts the master ready signal, and the devices see that, they do something in response to that, okay? what they do in response is put the data for that address on the data bus and assert the slave ready. Okay? So they're not going to do that until the master asserts the master ready. Okay, so the master is basically saying, okay, here's the new data. I'm gonna wait till everybody sees it, can decode it. Okay, go. If it's you, put the data on the data bus. Okay? So this is the cause, this is the effect. So when the device that recognizes that address sees this goes high, it says, okay, I can now put the new data on the data bus. The master's ready for that data. So it puts the data on the data bus and asserts it's slave ready. Okay? So we've got a bit of a delay between T1 and T2 as well. Okay? These are not necessarily equal intervals in time. Okay? There's no clock signal here where this is happening on clock edges. It all depends. Okay, so T2 to T1 here, well, obviously it's going to take some time for this master ready signal to propagate to all the slaves. So we have to take that into account, right? And of course, we've got delays in the slave circuitry before it actually loads its data on the data bus. So that takes that into account too. So here we have this is T2 and T1, yeah. Right, propagation delay from master to slave, and slave's circuitry is going to cause some delay there too, between those two times, T2 and T1. Okay, so now the slave has asserted its signal, it's put the data on the data bus, okay? After the master asserts its master ready, it is now monitoring that slave ready control line to see when the slave responds, okay? So the slave ready signal is going to cause an effect in the master. The master says, okay, this has gone high, that means I know the slave has put the data on the data bus. So now I can read it in. Okay, so the master's going to wait until it sees the slave ready go high. It now knows there's valid data on the data bus and it's going to read it in. Okay, so again, there's a little bit of the delay here between T2 and T3. Again, that involves bus skew. Right, difference in different propagation delays in different propagation lines. You've got to wait for all of the data to arrive at the master, no matter which device it comes from, okay? So it's got to take care of bus skew, and again, at this point in time, the master's going to read that data in. So we've got a little bit of flip-flop setup time there too that we have to include. Flip-flop setup time. That data has to exist at the input to those flip-flops for some amount of time for those flip-flops to successfully latch those values in. It can't just be there for a brief instant in time. It's got to be there for some amount of time called the setup time. So when the master now has read in the information, it drops its master ready, indicating, okay, I got the data, okay? That is going to cause a couple of things to happen. That is going to cause the slave to go, oh, okay, you got the data? Great. I can now take the data off the bus. Okay? So the other thing that's going to happen is when the master ready has dropped its data line, it obviously knows now, okay, this reads cycle is complete. I can now start the next read cycle by putting new address and command information on the address and control lines. Maybe read in the next value. Okay, so again, a cause and effect. So we've got a little bit of delay here as well. T4 and T3, right? Again, bus skew, because it takes different amounts of times for these signals to travel down different paths from one source to multiple sources. And this is very important because we don't want, for instance, we don't want the master changing its address information on the address bus before this has gone down to a low. Because if this address information changes, this address information as seen by other device changes while this is still high, those devices are going to go, oh, new address on the address bus, I gotta go and get the data for that, where it's already happened. Okay, so you need to wait a sufficient amount of time between here and here, such that this doesn't change until every device has seen this go to a low. Okay, yes, sir.
So the bus skew is not dynamic, right? Like it's a hardwired or hard-coded value somewhere
Yes,
in the processor?
that's my understanding. Yeah, because it's basically different propagation lines, propagation times over different lines, and that should be a static thing. Okay, so T4 to T5 is, yeah, you don't want the address command info to change while some devices still see the master ready high. Another way you can say that is erroneous addressing. Delay to prevent erroneous addressing. Because again, you know, all the slaves are always monitoring this master ready. And when they see it high, that says to them, oh, the slaves or the master's ready for the data. Okay? So you don't want this data, you don't want this changing over here, because when it changes, and this is still high as seen by a particular device, it's going to try to give that data to the master, which you obviously don't want. Okay, so that's asynchronous. Everything cause and effect, right? Master goes high, that causes the slave to do stuff. When the slave sets its slave ready to high, that causes the master to do stuff, right? When the master drops its ready signal, that causes the slave to do something. Drop its ready signal, take the data off the bus, and drop its ready signal. Okay, so there's a big, long description of this in the textbook, basically what I just said here. If none of this made sense, then probably reading the textbook is a good idea. Okay, any other questions about that? Yes, sir.
Would the bus cycle be about the same amount of time as the clock cycle on the synchronous? Like, what is the time period between the two? That's kind of what I'm curious about.
Well, it all, how quickly this here happens depends on these delays.
Yeah. But
So,
are they on the same order of magnitude, or is this quite a bit faster?
like just in general kind of
Yeah.
thing, right? I'm not sure I could answer that question. There's pros and cons to each. So, you know, some computers will use some will use the others. And we're going to talk about that briefly at the end. So it really depends on the application, which is always our cop-out when we're asked questions we don't know the answer to. Well, it depends on the application. But it actually does, because in some cases, it makes more sense to use this. In other cases, it makes more sense to use synchronous, depending on the devices you're connected to and the type of operations that are happening on the bus, right? Okay, so that is a basic synchronous, right? Master to slave. I guess it makes more sense to go, master to slave, slave to master, right? Master to slave, where should I say to? Where does it make more sense? So it does this data goes, no, it makes more sense to look. This signal has to go from the master to the slave, so there's one trip. This has to go back to the master, that's another trip. This has to go, so there's 3 trips if you want to look at it as 3 instead of 2, okay? Because these control signals have to go, there always has to be an acknowledgement of one control signal. So the master sends a control signal, the slave has to acknowledge it comes back. Then the slave sends a control signal, the master has to acknowledge, okay? Yeah?
But just to confirm, so at the edge of your master ready signal, are we saying that the data is ready to be sent?
Yeah, that's,
Or
no, that means the master's telling the slaves, go for it, the data's there.
like to take it,
Yeah,
and then at the slave ready, we're saying that the data has been received,
exactly.
and that's the acknowledgement
Exactly, yeah. Okay, so the asynchronous could be slower just because there's more trips back and forth down the bus to do one read cycle. Output operation, an output operation is similar. So let's say the processor is writing a data value to the main memory, okay? It's more or less the same, except in this case, when the processor puts the address and command information on the bus, that address is telling the device, hey, this is where you're going to store the data I'm going to send you, and the command information would be, well, this is a write, not a read. So I'm giving you data, I'm not reading data from you, okay? The difference here is at the same time, the master is going to put that data on the data bus, okay? Because it's writing it to the main memory unit, okay? Again, it's going to wait some amount of time between T0 and T1, right? And again, this is due to bus skew and decoding. Okay, this data is not going to arrive at every device at the same time. These address lines are not going to arrive at the data at every device at the same line. And even the different lines in the address bus, right? An address might consist of, I don't know, 16 lines, right? You've got a 16-bit address. Not every one of those bits will arrive at a particular device at the same time. That's also bus skew, right? So you've got to wait until everything gets there before you can expect the devices to respond properly. So that's bus skew, as well as decoding again. You're putting an address on the address lines. It takes every device some amount of time to decode that and recognize whether it's their address or not. So it waits to accommodate for that, and then at time T1, the master is going to assert it's master ready, telling all the devices, okay, there's valid data there, you should have had enough time to decode the address, everybody should have seen it by now you can go, okay? And again, it's full handshaking, so this causes something else to happen. It will cause the slave to go, okay, I acknowledge that you're ready and that there's data there, okay? So the device that recognizes that address is going to assert its slave ready signal, okay? So at time T1, the master asserts this. The slave that recognizes the address says, great, the data's there, I can latch it in. So it does that, okay? And then at time T2, the slave is going to assert its slave ready, and this tells the master, I got the data. This is basically telling the slave the data's ready. The slave reads it in, and once it's read in, it responds to the master and says, I got it, okay? So that difference between I've kind of written over it, T2 and T1, obviously it takes some time for that data to be loaded into the slave, okay? Okay, after the master asserts it's master ready, it's now waiting for the slave to respond. So when it sees that, it's going to say, oh, okay, slave got it. I can now drop my master ready. It responds by dropping its master ready, which is then going to be received by the slave. And the slave goes, oh, okay, you saw that, great, I'm done, okay? That is also going to tell the master, okay, I got the data, I can go on to the next operation. Okay, so now it's going to change the data and the address and command information, perhaps to write the next word to memory. Okay. Okay, so that it's kind of the same at the end here as a read operation. Okay, so it's always a back and forth. A change in one signal always causes the change in the other signal. Okay, and that's asynchronous buses output operation. Any questions about that one? This one here, right? If there's a delay after the master ready says, hey, the data's ready, if this device takes a long time to respond, no problem. The master waits, right? The master's not going to do anything until it sees the slave respond with the slave ready. So if one device takes longer, no problem. If a device takes shorter, right, if some device actually is a lot faster, well, then that's great. The master goes, oh, you got it already? Okay, I can move on, okay? So you don't the master doesn't have to always wait till the next clock edge before it does something. Trips going on, right? If we go back, okay, so pros and cons, as we were talking about. The good part of an asynchronous bus, it eliminates this need to distribute a clock to all devices in such a way that all those devices are seeing those clock edges at the same time. Okay, obviously if you're gonna be synchronized, everybody's gotta be on the same watch. And that's tougher than you might imagine to design a computer to do. That every device connected to that clock signal on the bus is actually seeing it at the same time. So if you can do away with that by using an asynchronous bus, that is an advantage. Less complexity, and you don't need to distribute a clock, which means less power. Okay? The other advantage of an asynchronous bus is delays can be easily accommodated. If we go back to, so that's another advantage of the asynchronous bus. The disadvantage is it can be a little bit slower because now there's a lot more round. So again, which one's faster? Well, the synchronous is really fast if you can make the clock really fast, right? So in a simple bus where the propagation delays are short, and you maybe only have 1 or 2 devices which are really fast devices, maybe synchronous makes more sense, right? Therefore, fast buses are typically synchronous. Okay, if you need a really fast bus, typically we make it synchronous because of these round trip delays in the asynchronous bus, but of course, you pay a price for that. You have to send a clock signal. You have to make sure all the devices see the clock signal at the same time. Simpler buses typically are asynchronous, okay? They're slow and simple or fast and complex, like you might imagine. Right, so that's asynchronous and synchronous. We're done for today and for a week. I'm going to put assignment number 3 on Canvas soon. It'll be due probably 2 or 3 weeks down the road. That will be the last assignment that will be marked. There will be assignment number 4, but that's just for you to work through on your own. You won't hand that in for marks, and of course I'll give you the solutions for that in preparation for the final exam. So have a great week off, and we'll see you in 9 days, I guess.